This question is about how roots of polynomials are related to one another. Normally, when you use the quadratic formula, you just substitute in, you get the roots. You don't worry about how they're actually linked together, but there's interesting formulae that arise and it can be useful to solve. In fact, we're going to use that method later on to solve this quartic at the bottom. So we start with a general polynomial of degree n. So it could be lots of different powers, and we're going to derive some results. We're also told that we can factorize this polynomial, which is actually always true. Even if you don't have real solutions, you could have complex solutions. But later on, we're going to be dealing with integer solutions. It's going to work out really nicely. But these are general results we're deriving to begin with. It then says, by considering f0, prove this formula here. Well, I'm going to take the first bit and find f0, and that's just going to leave me an because all the x's are just 0. And then if I put f0 into the second one, then I'll get 0 plus k1, that's just k1. 0 plus k2, that's just k2. You can see we're just timesing them together up to kn. And the result follows. Therefore, k1, k2 up to kn is equal to an. Done. Show also that this result is true. What I can do here is let x equal 1 in the second formula. So I'll put it equal to 1 in the first formula as well. F of 1 is just going to be 1 plus a1 times 1 to the n minus 1. That's just 1. So 1 plus a1 plus a2 all the way up to an. And if I do it over here, f of 1 is going to be 1 plus k1, 1 plus k2, up to 1 plus kn. And the result is going to follow. Just set them equal and rewrite it slightly so it's k1 plus 1 instead of 1 plus k1, but that's going to get us to here. Okay, great. We've got two results relating the roots of the polynomial. The roots are actually going to be minus k1, minus k2, but it's still, it's still valid what I just said. And then it says, give a corresponding result for k1 minus 1. Okay, I'm going to have to find out f of minus 1 now. So I'll put it into the top one again. I will get minus 1 to the n plus a1 minus 1 to the n minus 1 plus a2 minus 1 to the n minus 2 plus an. And by putting it into the second one, I'll get k1 minus 1, k2 minus 1, all the way up to kn minus 1. And I've got my final result. So just bring it together. We don't know if this is going to be 1 or minus 1. It will depend if n is even or odd. But it will alternate from then on as the power of n, as the power goes down by 1 each time. And then the last one was an again. Okay, there we go. So really, this is guiding us on the question. Rather than being the taxing part, we get these three results that we're now going to use. So find the roots of this equation, given that they're all integers. You could try and do some polynomial division for this. It could work out, but we're going to definitely follow through with the method that's intended to use these three equations to help us. In fact, they're going to simplify slightly because we've got that n is equal to 4. So k1, k2, k3, k4 is going to equal an, which is or a4, and this one here is a4. So actually we're going to get 576 as a first equation. Then k1 plus 1, k2 plus 1, and so on. That's going to be the sum of all of my coefficients. So let's deal with 576 plus 552. I get 1128. And then I've got 172 plus 22, or I can just add 23 because I can add the 1 and the 22 together. Gives me 5, 9, so 195. And then I can add them together. I can add on 200 to get 1,328, and then minus 5, 1,323. That is the product of when I add 1 to K1, K2, K3, and K4, times them together. Okay, we just got to use this final one now. Right, I'm now minus 1 to the 4 is going to be 1. Then I'm actually minusing the 22, adding the 172, minusing the 552, and adding the 576. So how best to do this? Probably best to kind of just do it in pairs, actually. This quite nicely becomes 150. So it's going to be 1 plus 150. And over here, I'm going to be left with 24. That's going to give me 175. So for my n equals 4, and for my particular quartic that I have, these are the equations that we generate. We're going to use these to find K1, K2, K3, K4. It's really important to use the fact that they're all integers. So basically, we're timesing integers together to give these numbers, or in some cases, we're adding 1 to them and then timesing them and so on. But we can use that to figure everything out, because I'm going to basically find out the factors of them. Now, the one to go with first, I think, is the simplest one. 175 is the smallest number. So let's write it as a product of prime factors. Well, 5 is going to divide into it, leaving me 35. So actually, this here is 5 squared times 7. There's a really nice way to find the number of factors when you have it in prime factor form, and it's to add 1 to each of the powers. We've got 2 and 1, add 1 to each of them, and times them together. It's going to be 6 factors for 175. But if we include negatives as well, you don't normally include negatives as factors, but here we're extending it. It's actually going to be 12, because these could be negatives. So there's quite a lot to consider. I'm going to write down ki minus 1, because I'm basically dealing with all the roots. There's nothing special about k1 or k2. Ki minus 1, and I'm going to write down my factors of 5 squared times 7. We can do this systematically. So we've got 1, and then let's do just the powers, just the 5 and the 7. And then we'll do 5 times 5, 5 times 7, and 5 times 5 times 7. Okay, I'm not going to forget the negatives, but I just wanted to make sure that I've got all 6. So if I want to know the different possible ki's, I'm just going to add 1 to each of them. 2, 6, 8, 26, 36, and 176. Just going to write down the same numbers now, but negatives. Hoping I'll be able to fit all of that in a second. All right, so the last one was a minus 175. So add 1 to each of them, 0, minus 4, minus 6, minus 24, minus 34, and minus 174. So it's this bottom row, they're my possible roots, but I've just used one of the equations to get them. So now I'm going to do similar for the other two, and I'm looking for, the same KI basically. I can eliminate them if it's not going to work. I mean, immediately I can eliminate 0, for example, because when I times them all together, I get a positive number. It can't be 0. Um, let's take a look at 576. 4 is going to go into it. 4 is into 5, go 1 and 4. We're going to get 144. So 576 is going to be 2 squared times 12 squared, which is 2 squared. Right, 12 is actually 3 times 4, so 3 squared times 4 squared, which is 2 to the 4. So I'm going to get 2 to the 6 times 3 squared. Actually, that's going to have a lot of factors. 7 times 3, 21 factors. So I might just leave that one for the moment. But we've got it there if we want it. 2 to the 6 times 3 squared. Let's take a look at the 1,323. I know it's a lot bigger again, but let's just see if it's any better. It has a smaller number of factors. So if I add the digits up, actually I get 9. 9 is going to go into this number. 1 remainder 4. 9 times 4 is 36. That's going to be a remainder of 6. 147. And then 3 goes into this. Actually, it's 3 times 49. So I get 1323 is going to be 3 times 3 times 3, or 3 cubed, times 7 squared. There's going to be 4 times 3, 12 factors. All right, there are more. And of course, we've got the negatives as well to deal with. I think we need to do that. So now it's ki plus 1 and ki. And I'm just going to write them down. Let's start with the positives and work systematically to get all 12. So we'll start with 1. That's a good shout. And then 3 and 7, just those kind of single powers. Then we'll go with 3 squared and 7 squared. And we'll do 3 times 7. So that's when we're timesing two things. Let's go with 3 things. So 3 cubed is 27. 3 squared times 7 gives 63. So that's when I'm timesing 3. I might miss one. I'll make, we'll just figure it out after. I've got 4, 5, 6, 7, 8. I've just got another 4. But we can bear in mind that when they get a bit too big, there's no way it's going to work actually. So I don't think we have to necessarily look through them all. Okay, I've kind of lost track of what I was doing. So we had, right, what if I do 27 times 7? That could give me one. So I'll get 49, then 140, 189. Okay, that'll be one. Immediately, that's going to be too big. I've got, of course, 1, 3, 2, 3. Well, I haven't done 9 times 49. That is a good one. Actually, the best way to do this is probably to do 9 times 50 to give 450, and then minus 9 to give me 441. And I've just realized I've missed one. I didn't do 3 times 49, give me 147. Of course, I've got all the negatives to deal with as well. I mean, I'm looking for any, where they're the same. I can immediately like just get rid of ones that are really big. Uh, and the 441 and the minus 441. Okay, I think the rest I'm gonna minus 1 from each of them now. So 0, 2, 6, 8, 48, so on. All right, there we go. And now I'm going to circle any ones. We've already got rid of 0, but I'm going to circle the ones along the blue row that are the same. So I've got a 2 in both. Okay, I'll circle them as I go, but it's mainly this now that I'm interested in. I've got a 6. I've got an 8. I've got a 26. I do not have a 36. So I can eliminate that one. I don't have 176. And then I've got -4. I do not have -6 or -24 or -34 or -174. We're nearly there. We've dealt with this one here and this one here. We just need to take a look at 2 to the 6 times 3 squared. So we've got to multiply to give that. But I don't now need to find all the possibilities for this. I can just look at the answers that I've got. And remember, I can get negatives as well. So I could use 2 - 4s potentially, for example. What we can see is that there's no way that 26 is going to be a possibility because it's not going to divide into 576. So eliminate 26, leaving us 4 possibilities. Now we can have repeated roots. In fact, we're going to have to here because 6 is the only one that has a factor of 3. So use 6 and 6 as 2 of our possibilities for ki. That's going to take us up to 2 squared times 3 squared. We just need an extra 2 to the 4, which is 16. So we can either do 2 times 8, or we can do -4 times -4. Okay, both of those are going to be possibilities. So either 6, 6, 2, 8, or 6. It's a little bit frustrating because we haven't seemed to actually eliminate it. But let's just see, because there's going to be a knock-on effect with some of the others. We just need to check that we can definitely know, because it's not just about what factors there are, it's how they then all play out together. So if I -1 from each of them, will I times to get 175? Let's find out. So check. So it would be 5 times 5 times 1 times 7 for this one, which is 175. So that seems to check out. 5 times 5 times -5 times -5. That is not going to equal 175. So at this point, we can actually reject that one. I could have checked the 1323 as well, but I just need it to not work there. I mean, maybe for completeness, I should just check the 1323 by adding 1. 7 times 7 times 3 times 9. Yeah, that's 7 squared times 3 cubed. So this one works out. All right, it's got to be said, that's quite involved, but it's a really interesting way to solve a quartic. Hope you agree. We're actually not quite there. Like it does say find the roots. So finally, the roots are going to be -6, remember, because it's minus k1, minus k2, and so on. -6, -6, -2, and -8. It's to be said, I think it would be much easier to do a polynomial division in this question by trying numbers out. You would only have to put in -2 to get a factor of x plus 2, which you could then divide. You get a cubic. You then have to try out some more again. Yeah, you'd have to then go with either x is -8 or -6. So it would be a bit frustrating, I suppose. But anyway, it's an alternative in theory. But this was a nice method. Well done on this question.